controller. This still red, and that's because we need to import. So let's just open up the POM for customer. Let's take this, Command C, and then within POM for fraud, let's paste it within dependencies, and then go back to fraud controller, and then I need to reload Maven. There we go. Now I should be able to import this. So import class. And you can see that this now, it's much better and neater, right? So we removed duplication around, and now we have one single place where we can have all the clients and all the models in here can be referenced throughout all microservices. And if any microservice wants to use this API or this client, they just have to include the module and then invoke it instead of duplicating code as we had before. Next, let's go ahead and test all of these changes. All right, let's go ahead and test our changes. So the first thing I'm going to do is to start the Eureka server. There we go, up and running. Now I'm going to start customer. There we go. Last but not least, fraud. Okie dokie. So now things are up and running. Now let me open a Postman, and still the exact same request that I've been using throughout this course. I'm going to send a person to customer and send, and have a look. 200 status code. So this means that the request did work. So now in here, if you look at fraud, or actually let's look at customer first, you can see that in here. So there was new registration. So this is the log for Jamila Ahmed. Then for fraud, we also have in here fraud check request for customer, and then one. So this is and then one. So this is Jamila's Ahmed ID. So this means that everything is working as expected, and you saw how we basically refactored our code. So we removed the REST template, and now we have this client, which any microservice that wants to use the API which fraud provides, they can just basically use this interface. Now, obviously, if you add more methods, so more endpoints into the fraud controller, so in here, fraud controller, make sure to also update the client in here, right? So that way you can have full access to the API. So this is it, to be honest. And also in here, so basically always remember, because this is an interface, so there is no method implementation, and rather you just copy this mapping in here, and this is what really matters, to be honest. And then the response as well has to be the same. But basically, if you want to learn more about OpenFA, go ahead and check my Spring Boot Masterclass where I teach all of this. But hopefully this was easy enough for you to follow. But if you have any questions, please do let me know. And before I just end this video, let me open up PG admin. So I just want you to see that this indeed is working. So if I view all rows, there we go. You see that we have Jamila Ahmed in here. If I also open up fraud, and then the fraud check history, and view all rows, there we go. Have a look. So this is working, and it's kind of cool. This is all for now. Catch me on the next one. All right, so inside of the customer service class, there is this to do in here. And what I want you to do is to create a new module, call it notification, and then try and use some logic. And then under the description of this video, you'll find the models required for you to send a notification, right? So any microservice can use this new microservice that you are about to create called microservice to send notifications. Now at this point, I don't want you to send the actual notification, and all I want you to do is to take the request and then store it in the database itself. So you're going to basically create the microservice, set up the Eureka server, add in the dependencies, set up the Eureka client. You'll also need to set up a new database in our database server, as you've seen before, as well as adding a new client under the clients module in here. So basically what we've done in here. So for fraud, we have a client for fraud. So also you need one for notification so that any microservice can use this client to send notifications. Now at this point in here, we're not going to use a message queue here. So this will come later, but for now, just use your Neo microservice to send a notification request and then stick that into your database. So what you should have is all microservices up and running, and then send the request from customer goes to fraud, and then if a customer is not a fraudster, send the notification. This is all for now. Give that a go, and I'll give you the solution next. All right, so for this exercise in here, I do have all the microservices up and running, including the Eureka server. And you can see that we have customer, fraud, as well as notification. Now, what I want to do is I'm going to send a request using Postman. So this is what you've seen so far. So Jamila Ahmed. So I'm going to send this request to customer, and there we go. So you can see that it was a 200 status code. Now, what this means is that the request did flow through. So in here, just ignore the load balancer, which we don't have at the moment, but the request went to customer, to fraud, and then customer did send a notification to our notification microservice. And currently we're just storing the request into the database. We haven't implemented Twilio nor Firebase. And also we don't have the message queue in here, but this we'll tackle later. But all I want to show you is that we are communicating between all of these microservices in here with their respected databases. Now, if I open up pgadmin, and in here, let me just refresh all databases, and then pretty much just open up notification, and then in here, schemas, and find the table. So here I've got a table called notification, right click on it, and then view data, all rows, and check this out. So here we have, so the notification ID is 1, the message is, hi Jamila, welcome to Amigos Code. The sender is Amigos Code. It was sent at this timestamp. And then in here, have a look to customer email. So this was jahmed@gmail.com. And then to customer ID was 1. So this is working beautifully. And obviously the data has been persisted in all of the different databases, including fraud as well as customer. So let me jump into IntelliJ quickly. And in here, what I've done is I do have this new client right here. And this is the OpenFake client, which in here, so if I show you, basically has a post mapping to API v1 notification. It accepts the request in here. And this guy will map into the implementation of the controller in here, which I'm logging. And then this has a send message, and then this forwards the request to the notification service .send method. It builds the notification using the builder, and then it persists it using the repository in here. And the model is as follows. So we have the entity, builder, all args, all these shenanigans, the ID, the sequence, and then these are the properties: notification ID, customer ID, email, sender, message, and sent at. So this is what you've seen. And inside of the customer service in here, so this is where things actually happen. So in here, if I put this full screen, so there's a format in here. So basically to do, this was basically send a notification, and this is where we send the notification. Now I do have a to do in here, which is make it a sync, i.e. add it to a queue, which we're going to handle later. And to be honest, this is it. And obviously, so within the pom.xml, I do have my new module, so on and so forth. Now I'm going to give you access to this commit so you can see exactly all the changes that I've made in case you haven't managed to do so. If you have any questions, please do let me know. Otherwise, catch me on the next one. Okie dokie. So in this section, let's learn about Spring Cloud Sleuth. So Sleuth provides Spring Boot auto configuration for distributed tracing. It configures everything you need to get started. So this includes where the tracer data spans, how many traces to keep, i.e. sampling, and if remote fields are sent to which libraries are traced. Now, this pretty much just adds a trace and span IDs to SLA4J MDC. And MDC stands for Mapped Diagnostic Context, and it pretty much provides a way for us to enrich data, i.e. the log data, so that we can correlate data across multiple services. So in here, you can see instrument common ingress and egress points from Spring applications, servlet filters, REST template, schedule actions, message channels, fake clients, and others. And if Zipkin is available, then it basically sends the traces via HTTP on this port right here, which Zipkin should be listening on. And we'll configure this in a second. So obviously you can basically have a look at the configuration, which I'm going to show you in a second. But to be honest, this is a very simple example. And what I want to do is, so if you click on learn, so in here, go to learn and then go to the reference docs. And you can pretty much just click on any of these links right here to learn more about it. So in here, if I click on getting started, and then what I want to show you is, so basically have a look. So the following image shows how span and trace look in a system. So if I zoom in, there we go. So in here, we have a request. And at this point, there is no trace nor span ID. So the span is the basic unit of work. And then we have the trace ID. So this is the ID which is unique on a different service. So in here, have a look. We have a request that is sent. So right here, there is no trace ID nor span ID. And as it goes through the service 1, have a look, the trace ID becomes X. So throughout the entire system, the trace ID will be the exact same thing. The request goes from service 1, 2, 3, 4, all the way back. And if you look at the trace ID, they're all the exact same thing. But what changes is the span ID. So as it lands on service 1, the span ID is A. Then as it transitions to service 2, it becomes B. Then you can have a custom span ID in here, becomes C. Then as it goes through service 3, becomes D in here. And you can see that you can also generate a custom span ID. But all the way back, you can see that basically it goes all the way to F. And then as it goes back, you can see that it basically matches from the request to response. So let's go ahead together and add this library. So in here, if I close this and let me go back and let's add Spring Cloud Sleuth to our microservices. So in order for us to install Spring Cloud Sleuth, let's together just take this dependency right here. So Spring Cloud Starter and then Sleuth. Now in here, what I want to do is within IntelliJ, let's open up customer pom.xml and let's add the dependency right here. Let's also do the same for Eureka Server. So within the POM and in here, add that in. Let's also do the exact same thing for, so don't worry if this is red because I need to reload in a second. So fraud. There we go. And finally, notification. So open up the POM and add a dependency. Now let's reload Maven changes. There we go. You can see that it's no longer red for fraud as well. Eureka server, as well as customer. Now, what I want you to do is go ahead and start all of these applications. So the server first, and then all of the microservices, customer, fraud, and notification. So let's start the Eureka server. There we go. Then let's also start customer. I will also do it for fraud, and finally notification. So now if I collapse this, and what I want to do is I want to open up Postman, and in here let's send our usual request to API v1 and then customers. We should get a 200. There we go. Now if I go back to IntelliJ and then open up this tab, so the run tab, and what I want to show you is, have a look. So remember when we added some logging. So let's go to customer first. So in here we have the log. Have a look. We have new customer registration, and then we have the payload. But what's important is, so this is actually added for us. So this is sleuth in action. Now this right here is the trace ID, and then this is the span ID, and the trace ID and span ID is added because of this log line in here. So we've done the same for all of the microservices in the controllers. Now the request from customer goes to fraud. So let's check fraud. So in here, have a look, we have another log message, and this is fraud. The trace ID is the exact same thing. So have a look, 77482. If I go back to customer, 77482. But what changes is the span ID. So this is now different. Then the request goes to notification, and have a look. So notification, so that's the name of the service. The trace ID is the exact same thing because it's one unit of work. But then here, the span ID is different. Now you can see that this information is actually added to every single log. But in here, so we don't have this information in here for these other logs because they're not ours. So now that we have this information, so the trace ID and the span ID across all microservices, next let's configure Zipkin so that we can see this information in action. All right, so now let's set up Zipkin, which is a distributed tracing system that helps gather timing data needed to troubleshoot latency problems in service architectures. If you have the trace ID in your log file, you can jump directly into it. So this is exactly what we have done. Now, what Zipkin allows us to do in here, have a look. So this diagram tells everything. So basically the request goes from A to Z. And in this example, you can see that they have 10 services in total with 13 spans. And this is the trace ID in here. So because we already have this information in our logs, we can basically configure Zipkin to visualize all of this data. So it also shows the dependency diagram, show how many trace requests went through each application. So you can see that it's kind of cool. So next, let's go ahead and use Docker to spin up a Zipkin container. So in order for us to get started with Zipkin, go ahead and click on the quick start in here. And you can basically see that you can use Docker. So you can just run this command, or Java, you can just say curl, and then you can run the jar like so, or you can run it from source. So what I want to do is I want to use Docker. So they have a link to Docker Compose. So click on that. And if I basically scroll down, you can see that they have a bunch of things, but here, have a look, they have Zipkin. So I'm just going to grab all of this, Command C, and if I open up IntelliJ and then close this, and in here, let me just collapse everything and open up our Docker Compose.yaml. And if I collapse all of these services, let's add Zipkin in here. So very last one. And basically, I'm going to leave the image as is. I'm going to remove the environment variables. So here you can actually use Zipkin to store data to a MySQL database. So let's not do this for now. So let's just remove everything. So in here, the ports, we're going to use this default port, and let's remove this as well. And we don't depend on storage. And for the ports, let me use double quotes in here because I think that's what I'm using throughout this file. And you can see that this is very simple. Now, open up your terminal and make sure that you are within your working directory. So if I type ls, you can see that we have docker compose.yaml. So now let's say docker space compose or dash compose if you are using the older version. So I'm using the latest. So compose is bundled with the docker command, and then say up. And finally, I want this to run in detached mode. So dash and then D. So now I'm going to press enter and have a look. Starting the Zipkin, and it already started. But if you're running this for the very first time, then it should actually pull down the image. So for me, it's up and running. And if I type docker logs and then Zipkin, have a look. So we have a bunch of logs in here, but in here we have HTTP localhost 9411. So let's just take this address and open up your web browser and then paste it in. And there you go. So you can see that we have a Zipkin server up and running. Currently, we haven't got anything sending tracings to this server, and that's what we're going to do next. All right, you saw that we have the trace ID and the span ID for every single log that we have. Now, what we want to do is to send those to this Zipkin server in here. Now, if you recall in this page right here, so Spring Cloud Sleuth, it says if Spring Cloud Sleuth Zipkin is available, then the app will generate a report Zipkin compatible traces via HTTP. By default, it sends them to a Zipkin collector service on localhost 9411. So if you want to configure the location, we can do it through this base URL. Let's open up IntelliJ and configure this. So for every single microservice, so in here, let's just basically, let me just close all tabs. And for every single microservice, so open up POM for customer to begin with. And in here, let's just add the dependency. And this will be Spring Cloud Sleuth. And this will come from the org.springframework.cloud. Now let me take this and add it to the Eureka server, just like that. Let's also add it to fraud. There we go. And finally, notification. There we go. Now, as always, let's reload the Maven changes so that it picks up the dependencies. And we should be good to go. Now, let's open up the main resources application.yaml, and inside of Spring, we can define the Zipkin URL. So here, I can just say, so one level before, I can say Zipkin, and then have a look. We've got base URL, and the default, have a look, the default is localhost and then 9411. So let's just basically be explicit. There we go. And this will be http://localhost:9411. So this way, if we are using Spring profiles, then we can basically change this according to the environment that we have. Now let me take this and add it to fraud, just like this. Also for Eureka server. There we go. And finally, customer. And there we go. Now, all we have to do is restart all the services. So let's start with the Eureka server and then customer, followed by fraud. And finally, let's restart notification. And there we go. So you can see that all microservices are up and running. And next, what we're going to do is test these changes and see how we're going to see all the traces in this Zipkin server. All applications have been restarted. Now let's open up Postman. And what I want to do is send a request to customer microservice. There we go. Status code 200. Now let's open up the Zipkin dashboard. And in here, what we're going to do is, so you can see that it says find a trace. So just pretty much click on run and then query and have a look. So have a look in here. We kind of have a bunch of requests, but one, so a few seconds ago, this is from the Eureka server, and that's because we did install it. But the one which I want to show you is this one here. So customer right here. So this one, which has 5 spans, and the duration was, so this was actually quite slow. I think it's because on startup, it takes a long time. But I'm going to send yet another request, so we see some improvements in here. But in here, what we can do is we can expand this, and you can see that this is the trace ID. And then these are all the microservices which are involved for this trace. So we have customer, notification, and fraud. So let's go ahead and click on show and check this out. So this is kind of cool. So you can see that the request started on customer, and this was the path. So post API v1 customers, and this is the time that it took right here. So this took 2.798, almost 3 seconds in total. But I think it's on startup, things are a bit slow. But then from customer, we made a request to fraud. So have a look. So at this point, somewhere in customer, we made a request to fraud, and this was API v1 fraud check, passing the customer ID. This was really quick. And then we send a notification in here. So after the fraud check, we then sent a notification. So we can click on this individual call in here, and you can see some more information. Have a look, the controller class, the MVC method, the client address, the same for post in here. And if I click on that, you can click on show all annotations, and then you can have more information. So the server start time and the finish time. So you can see that this is really cool. Also, you can basically download the JSON in here if you need to. But have a look in here. We have the duration, 3 services involved. The depth was 2, 1, 2, and a total of 3 spans with 1 trace ID. Now, what I want to do is send yet another request. So I'm just going to keep things as is, send, and this time you can see that it was much quicker. So in here, let me click to find a trace, run a query. It was this one right here. And now it didn't take 2 seconds. So this time it was super, super fast. Have a look. So this is really cool. So almost 400 milliseconds. You can click on show and you can see all the information. Now you can see that the Eureka server is actually generating a lot of noise. So let's click on show, for example. And depending whether you want this kind of information, if you need it, which I kind of doubt. Now, one thing is, so for this Eureka server, we're not storing the results to a database. So before you saw that we could store the results so that if this server crashes, then we have the data intact. So currently we're not doing that. Finally, if you click on dependencies in here, let me just click on search and have a look. So this is currently the flow for our microservices. So let me see if I can zoom in. No, zoom in doesn't really help in here, but basically I think there we go. So you can see the arrow which is going all the way across to fraud, and basically customer interacts with fraud as well as notification. Now, if you have a bunch of microservices, then you'll see all of these different arrows going to whatever direction they have to go. So this is pretty much distributed tracing, Zipking, and Spring Cloud Sleuth in action. Now, one thing which is kind of cool is that you can also, so if I click on Find Trace in here, so you can see that this is actually generating a lot of noise. So if I go to IntelliJ and open up logs, I basically want to grab this trace ID in here, go back, and in here search by trace ID, paste that in, and in here you see that we don't have the time it took to perform the database query, right? Because we are storing to a database from customer in fraud as well as notification. So currently we didn't configure the instrumentation for database calls, but this is something that you can do so that you have a better view on what happens in your backend. But you can see, for example, if this service right here, fraud, is taking, let's say, 2 seconds, then you know that there is something wrong in this microservice, and then you have to diagnose. The same for notification, right? So if notifications are taking a long time to be delivered, then you can basically use this to debug your applications. And finally, I forgot that you can actually search. So in here, if I click on Find a Trace, I can click on plus and then have a look. Service name, we've got 4 services currently. So I can click on, let's say, fraud, and you can even combine these. But if I run the query, have a look, these are the results. So this is pretty much all for this section. If you have any questions, please do let me know. Otherwise, let's move on. In this section, let's learn about load balancers, and I'm going to show you how to configure one and how it works in detail, and also show you the best way of you taking advantage of load balancers as you deploy your applications. So in a typical application, you have the clients, this is the internet, and this right here, let's say that this is a VM somewhere on the cloud with this particular public IP address. Now, so far we've been creating microservices, and we have one which is customer. So this handles customer registration. Now this right here, so this setup where you've got 1 client or 2 clients or maybe 3 clients using one particular instance to register the application is absolutely fine. If you are working on a personal project, then this is fine for you to build because the setup, it's really easy. All you have to do is you spin up an instance somewhere on the cloud with a public IP address, and then you can access this instance. So let's say that your application is becoming popular day by day, and it's actually receiving more traffic. So let's say that you went from 1 or 3 clients to 10,000 clients using your application. The problem that you're going to have is that 1, you either need one really big machine, i.e. one VM with 32 or 64 cores, lots of RAM, and other high spec, right? So this might solve the problem temporarily, but still doesn't scale. If you go from 10,000 clients to 100,000 clients, then basically you kind of have to do something else. So usually what you do is you have multiple replicas of your application. So in this case, customer. So here you can see that now I do have 3 instances. So this is one instance, another instance, and then yet another instance. Now, the problem here is that these clients right here that are connecting to your backend system, right? They don't know which VM to connect to. So if they all connect to this one, then this one will run out of resources, leaving you with these other instances receiving no traffic. Or maybe you could actually implement some logic in here that has a list of all IP address for all of your instances, so on and so forth. But no one does that. So how are you meant to access your applications in this scenario? Well, this is what load balancers solve. So to fully understand this, let's take our architecture that we currently have and let's introduce load balancers so you see how it works. So in here, this right here is my private network in here. And what I have is an external load balancer. So this external load balancer, this is the main entry point for any client that wants to connect to your applications. So instead of clients going directly into customer or fraud or notification, you say the main entry point is through this external load balancer. Any traffic that goes from the internet directly into these instances inside of the private network will be blocked by the firewall. So a request comes in through the load balancer, and the load balancer is actually quite smart. So there's a lot of things that you can configure within it. But let's say that you want to send a request to customer. So this request right here is sent to this other load balancer. Now, this is an internal load balancer, and the reason is because you might have multiple instances of customer or fraud or notification. So the same problem that you are solving from the outside world connecting to your services is going to apply within the private network, because these communications right here, so this is an internal communication, and this is a communication from service to service. So you also need an internal load balancer. Now, the configuration between this load balancer and this load balancer will be a little bit different, but I'll explain more in details in a second. And to be honest, this is load balancers. Now, there are a lot of things that we have to take into account, such as TLS, certificate management, authentication. Where do you authenticate the requests? Do you authenticate the requests within every single microservice or within this external load balancer? Do you terminate TLS in here or through these services in here? How do you make your load balancer high available? Meaning that it's always up and running no matter what. Is it cross-region if you're running your application in multi-region or not? Logging, caching, path-based routing. So in here, you see that instead of having multiple external load balancers for each of our applications, we can just have one. And then based on the path, we can redirect the request to the appropriate internal load balancer. Now you can see that this actually is quite a lot of work to do, and most often when you run applications in production, you should choose a managed load balancer instead of managing your own, because this right here is the main entry point for your application. So if this load balancer dies, right? So let's say you are managing the load balancer. If it dies, then you can see that this is a Sev1 incident immediately, right? So we actually let cloud providers manage this for us so that we can just, again, focus on our microservices and our own business logic. So let's take a look at the cloud load balancing provided by Google Cloud. So in here, you can see that they give you some information about it, what it is. But in here, let's just take a look, have a look. Over 1 million queries per second. So you can see that if we were to manage our own or set up our own, then it can be quite challenging for us to reach these numbers. Seamless auto scaling. So can scale as your users and traffics grow, including easily huge, unexpected, and instantaneous spike. So maybe there's an advert going on, so you can expect a bunch of traffic coming your way. So this scales out for you without you having to do anything. Internal load balancer. So as I was saying, for internal services, so you can see support for cutting edge protocols, HTTP, HTTP2, gRPC, HTTPS as well, load balancers. So you can see right here, cloud logging, TCP, SSL, SSL, offload, affinity, CDN, and the list goes on and on and on. The same with AWS. So they provide either an ALB or gateway load balancer or network load balancer, and they give you some information how it works in here. So the same thing as the one provided by Google Cloud. And if I click on features, for example, have a look. So these are all the features that it provides. So redirects in here, path-based routing, IAM, health checks, SSL offloading, clouds as a target, logging, so on and so forth. HTTP header-based path routing. So this is really important and one that we want. And you can see all the protocols listeners. The same with the targets, whether you want to target to an IP, an instance, or a Lambda. So this is a really cool feature for serverless applications. So you can see the benefits of a managed database. Now, if we were to, oh, actually, I didn't even show you. So SSL, so certificate management. So all of this is actually integrated. Now, if we were to manage all of this ourselves, you can see that it's quite challenging. So also Nginx, so this actually provides you a load balancer as well with some of the features that you'll see, and you can read more about it, how to configure one with Nginx if you want to learn how all of this stuff works. But basically this is why you really should use a fully managed load balancer when running your applications in production. Next, let's go ahead and learn how the load balancer works. Let's say that we have two identical microservices in here. So they're both healthy. Now, how does the load balancer knows to which microservice to send the request? This is done through the load balancer algorithm that you choose. Now, the most common one is round robin, meaning that it will distribute the request sequentially according to the number of servers that you have. So if you have your very first request, then the load balancer will send the traffic to this customer microservice, so this very first one here. The next request will be sent to this other microservice. The third request is sent back to this microservice. The fourth request is sent back to this one, so on and so forth. So you can see that it kind of alternates as requests come along. Now this is one algorithm and it's known as the round robin. So it basically distributes the requests sequentially according to the number of servers that you have. But obviously there are many algorithms that you can choose from. So you've got round robin, which requests are distributed across the groups of servers sequentially. You have least connections. A new request is sent to the server with the fewest current connections to clients. You've got least time. Send requests to the server selected by a formula that combines the fastest response time. You've got hash. Distribute the requests based on a key you define, maybe such as the client IP address, which means that when the client makes a request, it is almost guaranteed that the request will land on the same server. Then obviously you can take advantage, maybe if you are storing, for example, a session, or you are caching some data for that particular user, then this could be a good approach. But also there is something known as the consistent hashing. So this is when the number of servers increase or decrease, then obviously because the hash function will change because it's a modulus on the number of servers, then you can expect some requests to end up in a different server. So here IP hash, so this is pretty much what I've just described. And then you've got random with two choices, pick servers at random, so on and so forth. And this right here, I'm taking this from Nginx, which is a really great explanation. But depending on the load balancer that you choose, then you should check the available algorithms that they have to offer. So let's say that you have two microservices behind the load balancer. So one which handles PDF requests, so you can generate PDFs for your customers, and another one for handling customer registration. Now, in order for these to be considered as healthy targets behind the load balancer, there must be a way of this microservice and this microservice to tell the load balancer that they are in good shape to receive traffic. And this mechanism is what's known as the health check. So if the health check for any of the microservices is okay, i.e. status code 200, then it means that whenever a request comes from the clients through the load balancer, if the microservice, so let's say that this microservice is healthy, then the load balancer will send the request to this microservice. The same with this one. So if this is healthy, it will send the request. Now, in here, you can have different ways of defining health checks for your application. So maybe this PDF service doesn't have a database. So therefore, the only health check that you can do is mainly just check that it's up and running. So you just send a request to the /health endpoint. And if it returns a 200, then it's good to go. Maybe this one, the health check, might be a little bit different. So because this microservice might depend on a database, then the health check will be, am I running okay? But also, can I get a connection from this database? Then if all of these checks pass, then we send a 200 back to the load balancer. Otherwise, we say, nope, we are really having trouble, so I cannot accept any traffic. So these are health checks. Since we are using Spring and Spring Boot to develop our microservices, Spring Cloud gives us a gateway that we can use. So this is pretty much an API gateway, and it serves as the main entry point for our application, and it aims to provide a simple yet efficient way to route APIs and provide cross-cutting concerns such as security, monitoring, metrics, and resilience. So almost all the points that I've mentioned about, it actually gives you all of it. Now you can see all the features in here. So it's built on Spring Framework 5, Project Reactor, and Spring Boot 2.0, able to match routes on any request attributes. Predicates and filters are specific to routes. Circuit breaker integration, which is kind of cool. So if for whatever instance the microservices behind the load balancer or the API gateway are unavailable, then you can basically send a default response to your clients. So Spring Cloud Discovery integration, easy to rewrite predicates and filters, request rate limiting, which is kind of cool, path rewriting, and others. So in this section, let's learn how to set one of these up. And I just want to be really clear with you. I'm not going to fully teach you how to configure this because, as I said, this can be a really difficult job. And instead, what you should do if you are deploying your applications, you should use a managed load balancer, such as the one provided by Google Cloud or AWS. So again, always use, for example, an application load balancer or an ALB because it takes all of those concerns away from you, allowing you to focus on your microservices and business logic. But still, let me show you how to set one of these up so you can see that it's really straightforward. But again, you should never manage a load balancer yourself. And people usually don't. And as you'll see with Kubernetes, when you use services, it actually can spin up an application load balancer depending on the cloud provider that you are using, which is kind of cool. So you just give it a YAML definition and off it goes, and it provisions a load balancer for you. So if you have any questions so far, please don't hesitate to let me know or ask on Discord. But let's go ahead and learn how to set this up for our current architecture. So let's go ahead and create our API gateway. Now for this, let's create a new module. And in here, let's just say next. For the name, I'm going to say API Gateway, so G and then W, and then just say finish. Now within this pom.xml in here, we're going to have a couple of dependencies. So let's just say dependencies, and one that we want, and the one which is really important, is the Spring and then cloud dash starter dash and then gateway. So this will give us the API gateway, and you can see that it comes from the parent POM. Now let's also add in the Eureka client. So let me just put this full screen, just like that. Let's also add in the sleuth as well as Zipkin. There we go. So you can see that all of these dependencies, so you've learned about these three dependencies, so Eureka client, sleuth, and Zipkin. Now we are learning about the starter gateway. So now let me just reload this Maven changes, and this should come up fine now. Just give it a second. And there we go. Now let's open up project, and within API gateway, within source, main Java, let's have a new class, and this will be API GW and then application. And in here, let's annotate this with @ and then Spring Boot application. Let's also have the main class. There we go. And within the main class, let's just say Spring application dot run, and then pass API GW dot class as well as the args. Now, one thing which I'm missing is the default package. So here, let's just say package com.amigoscode dot API GW, and let's put this inside. There we go. This is much better. And finally, what we need to do is enable the Eureka client. So just before the application, so at enable and then Eureka and then client. There we go. Now let's open up the resources, new file, application dot and then YAML, and let's define the application name. So application name, this will be API gateway. Let's also define the port. So this will be port, and for the port, I think 8083. I think we're not using this, so let's just this be the very first thing. And finally, let's have the configuration for how to connect to the Eureka server. So let's just open any of these microservices, open up their application.properties, and let's just take all of this and then go back, paste that in. We also need Zipkin. So oops, so Zipkin should be within Spring. So in here, there we go. And we are good to go. Finally, let's just copy the banner, paste it in, and then let's change this to API gateway. So let me just select everything there, and I already have it in my buffer. So there we go. And we are good to go. Next, let's go ahead and configure our load balancer so that whenever we send a request that is meant to be for customer, then we send it to our customer microservice. So in order for us to configure the API gateway so that whenever a request goes to customer, then we should basically route the request to the appropriate microservice. Within Spring, we have so in here, cloud. And within cloud, we have gateway. There we go. And what we want to do is we want to set up the routes. So here, just say routes. And this is a list. Now, the way that we define a list using YAML is as follows. So here, we need to pass the ID. That's the first thing. And I'm going to say customer. And then we'll also have to pass the URI. Now, the URI, this will be LB, column, and then customer. And finally, let's define the predicates. And this takes the path right here equals to, and this is basically whenever we send a request to API v1, so v1, and then customers / and then pretty much anything, we want to send it to customer. And in fact, this should be / so lb : / and then customer. Now this customer right here is the following, and within my Eureka server, so have a look, we have currently customer, fraud, and notification. So lb and then customer is this guy right here, and then this will distribute the request to the appropriate node which is behind this application in here. So in here, a request will reach the load balancer, and then anything which is mapping, so API v1 and then customers, it will be routed to this customer microservice. So currently we're not doing anything for fraud because we don't want to expose fraud as yet. But if you want to expose fraud, you pretty much copy this right here, and then you basically say that you want a new route for and then fraud, and then you change this to fraud right here, and this will be the path that you want. And bear in mind that this is an array of predicates, but currently we don't want to expose it for fraud, so we just want for customer. That's all for now. Catch me on the next one. Okie dokie. So let's go ahead and pretty much just open up the API gateway application, and let's run the main class. So hopefully we've configured everything properly. So run, and also make sure that all the other microservices are up and running. So here we should see that the API gateway should be running. There we go, up and running. And we have the API gateway in here powered by Spring Boot. And in here, if I scroll down, you can see that we have started API gateway, and the port is 8083. So that's the one we've configured. Now, what we're going to do is let's open up the Eureka dashboard. And in here, so if I reload this, we should see the API gateway now. And what I want to do is, instead of sending the request to customer directly, so I said that customer is within the private network and we should never access it directly. Now, currently we are running things on localhost, and we can run it directly, but as you deploy things, you should never be able to access any of these microservices from the outside world. You should go through the main entry point, which is our load balancer. So let's open up Postman, and in here before, remember, we said that 8080, so this is the port for customer, but now we want to send the request to 8083. So this is the load balancer. And then remember this, so this path, when the API gateway sees it, it will forward the request to customer. So basically, if I say /customers / and then 1, for example, or any other path, this will be sent to customer. So if I send this request, and check this out, we have a 200 status code, which means that the request went to our load balancer, and then from the load balancer, it did send the request to customer. So let's open up Zipkin, and in here you can see that there was a post to the API gateway. Let's click on show and have a look. So the request went to the API gateway, then the API gateway sent it to customer. From customer, it went to fraud, and then from customer, it also went to notification. And you can see that this is working beautifully. If you have any issues setting this up, please do let me know. Otherwise, catch me on the next one. So far, we have this implementation in here where we have the load balancer, customer, fraud, and also notification. Now, in here, we have got no asynchronous communication within these microservices. So fraud, nor customer to notification. Now, let's say that notification takes, let's say, 10 seconds to send a notification to our customers. Now, this means that from the time that clients are using our application, there will be a delay of 10 seconds in total, plus some milliseconds and whatnot. But in general, 10 seconds. Now, this is a very bad user experience. So maybe Twilio is having an incident, or Firebase, they're having an incident, and they can't really deliver messages for now, and it's taking them 10 seconds. Now, you can see that we are depending on Twilio and or Firebase, because this call right here from customer to notification, it doesn't have to be immediate. So it can have a delay, right? So whether the customer receives the notification or SMS after 1 second, 2 seconds, 3 seconds, 1 minute, it doesn't really matter. What matters is from the point that when the customer registers into our system, in here, customer talks to fraud. So this call right here cannot be asynchronous because we need to check whether it's a fraudster or not. If it's not, then this call right here indeed can be asynchronous because we don't depend for any other checks to be performed. Currently, this is a problem that we need to solve. Even more, let's say that customer right here is sending lots of traffic and we only have one notification instance. Now, what happens if notification gets too busy? Well, the notification won't be able to handle the requests coming from customer nor from fraud. It's just going to be too much. Well, you might be wondering, okay, maybe we can add a second instance. So just like that. Well, it is fine, but again, still a problem because you don't know whether this will be enough. And the same, let's say that you kind of want to have 10 servers for notification. Now, this is not using resources correctly because one, it doesn't scale correctly, and also things are not asynchronous. And even worse, let's say that we kind of need to perform an upgrade on notification. So we found a bug, and in the meantime, a bunch of requests are coming through. Now, if notification, so in here, so if we get rid of notification, then it means that the entire call from here to customer, fraud, and in here notification, 0 instances, this will fail. And at this point, we already registered the customer. And the only thing that we need to do is just to send the notification. But if notification is not up and running, then the customer will be created and the response that the client will get is a 500. And you can see that this is not feasible, right? So this is pretty much what a message queue allows us to deal with. Next, let me show you the example where we slow down notification and see what happens. Within IntelliJ, I do have all of the microservices up and running. So if I click on run, you can see that I do have customer, fraud, as well as notification. Now let's send a request to the API gateway, and before the request reaches notification, let's stick a breakpoint in here. So notification is running in debug mode, and I've got this breakpoint in here. So let's open up Postman, and in here, we're going to send this payload to the API gateway, which is listening in on port 8083. And from here, you can see that this is very quick. So it takes about 941 milliseconds, give or take, right? So this is when the request goes from one end to the other. Now, if I send this request, So this actually took me to this breakpoint. And now let me go back yet to Postman and have a look. This request right here is hanging. Now, what I'm trying to simulate is the case where the request reached notification. And by the way, this is without the message queue right here. So the request reached notification. And now let's say that Twilio is taking forever, or Firebase, they are taking forever to process our notification. Now you can see that Postman is actually hanging in here. So it's saying send the request and it's waiting forever. Now if I was just going to basically remove the breakpoint, but I can see that this probably was a timeout. And before I send the request, so let me just go to notification, and in here, let me just resume this, and eventually it sends the notification. But let me go back yet again, and let me send. So let me just wait for a second, and you'll see that. So let's just say that Twilio was having a bad day and they took some time to process the notification. Now it worked. Let's just resume back to Postman and have a look. 18 seconds to process our request, which is insane. So you can see that we have a bottleneck in here. Now within Zipkin, you can see that in here I do have the calls. So this one was the first one that took some time, and then this one was the one that took 18 seconds. So if I click on the show in here, now I want you to check this out. So the request from the API gateway took 18 seconds. Customer made a request to fraud. And have a look, fraud, you can see this line right here, which is barely visible. So this was super quick. So if I try and click on that and have a look, fraud controller, and if you show all annotations, you can see more information. But this was really quick. So this call right here was very quick. And the problem really lies within notification, which is taking 18 seconds. Have a look, this line is actually all the way through the end. So this is the bottleneck. So you can see also why having Zipkin is really important, because we can visualize all of this stuff. Now this is when the message queue comes to rescue. So at this point, if we stick the request inside of the queue, it returns an acknowledgement back to the sender, in this case customer. And then if notification is taking a while, then basically we don't have to wait for 18 seconds as you've seen, right? Because we know that eventually the notification will be processed. So this is why we need to use a message queue. If you have any questions, please do let me know. Otherwise, let's move on. So you've seen why we need a message queue, and AMQP stands for Advanced Message Queuing Protocol, and it's a protocol that enables conforming clients applications to communicate with conforming messaging middleware brokers. Now, what are these brokers? Well, a broker receives messages from publishers, i.e. these are applications that publish messages, and they're also known as producers, and it routes them to consumers, i.e. other applications. So the broker receives messages from publishers and it routes them to consumers. Now, since this is a network protocol, the publishers, consumers, and the broker can all reside on different machines. So you can see how you can decouple your applications. So in here, you've seen that we have these microservices, they talk to each other. And currently, if customer sends a notification to the notification microservice and notification is down, or notification is having trouble handling requests, then you can see that this can be a bottleneck for our application. And instead, what we do is we use RabbitMQ in this case. Now, I'm going to touch on RabbitMQ, but later you'll also see Kafka. And I don't want to go too much in detail about the difference between these two, but for now, let's just focus on RabbitMQ. Now, the broker is everything that resides within this rectangle in here. So the way it works is if fraud or customer, they want to send notifications to the notification microservice, they send a message, and the message is pretty much the payload, right? So the JSON payload in our case. Now this message here gets sent to the exchange, and the exchange job is to route the messages to the according consumer. So in this case right here, you can see that this exchange forwards these messages coming from fraud as well as notification, and then notification consumes the messages from this queue right here. So fraud, customer are producers. The messages go through the exchange. The exchange routes to the queue. Inside here, this is the broker. And then outside, we have the consumer, which can be any microservice that is configured to pull messages from this queue. And with this architecture, we gain a ton. So one is loose coupling. So fraud, customer, notification, as well as the broker, they can live on separate machines. And since we are following the microservice architecture, this is actually loose coupling all of these services together. The other thing is performance. So we gain performance. Now, if notification is down, let's say that notification is down, right? So let's say that we don't have a consumer right here. Now, the cool thing is that fraud and customer, they can still send notifications. And at this point right here, the exchange right here receives and then puts it inside of the queue. Then once notification is back up, it pretty much just reads the messages that were hanging in the queue. And the benefit is that our clients don't even experience that notification was down. Also, we can start sending messages asynchronously. So if, let's say, Twilio is taking 20 seconds or more, it doesn't really matter, because from our point of view, if any producer is able to publish messages to the exchange, then we are good. We can also scale in a way where if you need to run this as a cluster, 2 or more machines, you can absolutely do it. And you should run multi-AZ whenever possible. Also, the benefit of using RabbitMQ is that it's language agnostic. So let's say that fraud right here, it's written in Java, and notification is written in Golang, for example. So it doesn't really matter, right? Because all notification needs to do is to be able to pull messages and then transform the payload into whatever struct, for example, if you're using Golang, or if you want to use Python, then it basically takes the messages and transforms it in a way that it wants. Now, messages also, they don't get removed from the queue unless the consumer acknowledges that it has received the message, which is a good feature, right? So if notification has issues reading from the queue and the broker doesn't receive an acknowledgement, then the message is still intact. RabbitMQ also offers as a management UI, which you'll see in a second, and the community has built lots of plugins, and you can run RabbitMQ on the cloud, which is a good thing, right? And you'll see how we're going to run RabbitMQ through Docker. And as you know, if you Dockerize your applications, then it's really easy for you to deploy on whatever cloud provider you want, whether it's AWS, Azure, Google Cloud, Linode, and others. So this is pretty much how everything works. Next, I want to dive deeper into how producers are able to produce messages, as well as the different types of exchanges. So when it comes to decouple microservices and provide asynchronicity between them, as well as resilience, there are a couple of big players in this field. One of them is Apache Kafka. Now, Apache Kafka is open source, and I believe it was initially developed by the guys at LinkedIn, and it's basically used by a lot of companies. So it provides high throughput, it's scalable. One cool feature here is that it has permanent storage. So you can store streams of data safely in a distributed, durable, fault-tolerant cluster in here. So something that RabbitMQ, for example, does not provide. Then it's also high available. So you can stretch clusters efficiently over availability zones or connect separate clusters across geographic regions. Now, Kafka on its own, it's a big beast, I have to admit. But still, I'm going to basically show you how you're going to use Kafka with Spring Boot at a later stage. Then what we have is RabbitMQ. So RabbitMQ is the most widely developed open source message broker. For this course, we're going to begin with RabbitMQ due to its simplicity of getting started, understanding its concept, and the integration with Spring Boot will be really straightforward, as you'll see. We also have Amazon SQS. So Amazon SQS stands for Simple Queue Service. It's a fully managed message queuing service that enables you to decouple and scale microservice distributed systems and serverless applications. So if you are deploying your applications to AWS, then this is a great solution because it's fully managed. Now, one disadvantage of using SQS is that, let's say that you want to port your microservice architecture to Google Cloud. So recently, there were a couple of regions of AWS that were down, for example. Now, in this case, if you are deploying to multi-clouds, i.e. you're deploying to AWS as well as Azure and maybe Google Cloud, let's say that you've managed to deploy to all those three at once, right? So it's a very difficult job, I'm not going to lie, but let's just say that you've managed to do it. Now, if you are tied to SQS, then you can't really move across any other cloud provider because SQS is AWS specific. Whereas maybe if you're running your own Kafka cluster or RabbitMQ, then you have more flexibility in here. So usually you'll see that you have teams that are dedicated for making sure that your cluster, i.e., either using Kafka or RabbitMQ, that these are always up and running. Because again, if they go down, so in here, so if you lose your message queue, then you can see that again. So if this goes, then you have a big problem. But usually it shouldn't be a problem because when running Kafka or RabbitMQ, you want to run in multi-AZ, for example, right? Multi-availability zone. So if one availability zone is down, then no matter what, things are still up and running. So you'd never have one single message queue for all of your microservices when running in production. And before I forget, I'm going to leave a link where you can learn more about the differences between Apache Kafka, RabbitMQ, and SQS so that you have a better understanding of these tools. If you have any questions, drop me a message. Otherwise, let's move on. When producers want to send messages, these messages will first land inside of the exchange. The exchange then forwards the messages based on a routing pattern. Now, this is possible through the binding. The binding is what binds the exchange to a particular queue. So you can have as many queues as you want, and you can have also as many exchanges as you want. But the thing is, you can attach multiple queues to one exchange. Now, this exchange right here has different types. You can have a direct exchange, a fan out, topic, headers, as well as one which is special to RabbitMQ, and it's the default, and it's known as the nameless exchange, where the routing key is equals to the queue name. If I open up IntelliJ, and in here, this is some configuration that you're going to learn in a second, but here I'm defining the exchange that I want, I'm defining the queue that I want, and also the routing key. So here I'm saying internal notification routing key. So this is the internal exchange that I have, and I'm saying that if anything goes through with this key, then I want to route it to this notification queue. Then the producer, on the other hand, all it has to do is send the payload to the exchange, providing the routing key. So providing the routing key. So providing the routing key, and this is configured through the binding to send to this particular queue. So since you saw some code, now this should make sense. When the producer sends a message to the direct exchange, which is this one right here, it means that the routing key as well as the binding, they have to be the same. So when they're the same, if you send a message, so let's say that we have a message, so let's just take this guy outside. For example, if you send a message, it will land into the exchange, and from the exchange, it will land into, let's say, this queue in here, right? So this is when the routing key is equal to the binding. Then you can see that we have the fan out exchange, which means that if the producer sends a message, this message will be fanned out. So here it will be sent to all queues, just like that. It fans out the messages, so every queue will receive the exact same message. Then we have the topic exchange, and this is mainly for partial matches. So when you send a message, if the routing key is full.bar and then the binding, so let's say that you have a binding in here, and let me just add some text, and this is full.star, and when you send the message in here, you specify that you want to say full.bar right here. So this is a partial match, right? So full.bar matches this binding, therefore this message will be sent across in here. Then you have the header exchange, which uses the message header instead of the routing key. So obviously this is a bigger decision that you need to make according to your needs, but this is pretty much how it works. And I actually almost forgot is that you have a special exchange which is only specific to RabbitMQ, and it's the nameless exchange. And this is when the routing key is equals to the queue name. So if you have a message which has been sent, and this message right here has the routing key as app b and then q. So because we have a queue with this routing key, it gets sent to this queue right here. And to be honest, this is pretty much how everything works. Obviously, you can grab the diagrams so you can basically check for yourself. But if you have any questions, please do let me know. Otherwise, let's implement all of this. In order for us to have a RabbitMQ locally, let's use Docker. Open up your docker compose.yaml, and within you can see that we have Postgres, we have pgadmin, Zipkin. So right after it, let's just take this in here and let's just paste that in, and this will be RabbitMQ, just like that. Then for the image, RabbitMQ column, and then let's just use the same version so that if we have any breaking changes, things will still work. So 3.9.11 dash and then management and then dash alpine. So we get the smallest version. For container name, this will be RabbitMQ. For ports, we want to expose 56 and then 72. So 56, 72. The same on the other side. So the first port is the host and the second is the container. Now this port is what applications will be connecting to, i.e. microservices. So if we want to publish a message to a queue, we're going to use this port. Then we also want to expose the 15672, and this is the management port, just like that, so that we can use the management console. And to be honest, this is everything. And I've just noticed that this should be al and then pine. So al and then pine. Now let's open up our terminal. Make sure that you are within the working directory. So ls, you can see docker compose.yaml. Now type docker compose up dash and then d for detach. Press enter. And this, now you can see that it pulled the image and it has started. So for you, if it doesn't pull as quick as mine, it's because I think my one was cached. But you can see that the RabbitMQ container is up and running. Now let's take this port, so 15672, and open up our web browser, say localhost colon and then 15672. Press enter and check this out. So now the username for this is guest and the password is also guest. Press enter and I'm going to save this password, and ta-da, you can see that we have RabbitMQ running locally. Now in here, there's a bunch of information. So you can see connections, you can see channels, exchanges. So I've explained about exchanges as well as queues. So if I click on exchanges, by default, we should see few exchanges right here with different types. So these are defaults and we don't have to worry about. And if I click on queues, so you can see that we have no queues so far. If you have any questions getting this far, drop me a message. Otherwise, let's move on. All right, so let's go ahead and build the building blocks so that we can publish messages to the exchange, and so that we have the ability of listening messages from a queue. So let's open up IntelliJ, and in here, let's create yet a new module. Next, and here, let's just simply say advanced message queue. So I'm just going to leave it as AMQP. Now I'm going to finish, and inside what we need is to bring in the dependency that allows us to have the RabbitMQ classes. So for that, so within dependencies, let's just say dependencies, and within dependencies, we're going to bring in, so dependency, and this will come from Spring dash and then starter, or actually boot dash and then starter dash and then advanced message queue protocol. And this comes from Spring Boot, just like this. Now let's open up, and inside of main Java, let's have a new package. We're going to name this as com.amigoscode.advanced message queue protocol, and inside let's have a class, and we're going to name this class as RabbitMQ and then config. Now this class will serve as a configuration, so let's annotate this with add configuration, and inside we need a couple of things. So the first thing that we need is the ability to be able to publish a message to a queue. And to do that, we need to have a bin, and this will be advanced message queue protocol, or in fact, I need to reload in here. So always remember to reload the Maven changes, otherwise you won't get the classes needed. So there we go. And let me just close this. So now here, advanced message queue, and then protocol, and this will be template. So AMQP and then template. So this is an interface, and I'm going to name this as AMQP template. And inside, we're going to have Rabbit and then template. And by default, we actually get this Rabbit template. But because I want to customize it, then we have to do this way. So this will be equal to new and then Rabbit template. Now this guy here takes no parameters or a connection factory. The connection factory, we can inject it. So private final and then connection and then factory, just like that. And here I'm going to say at all and then Args constructor and job done. So let me put this full screen, and now I can pass the connection factory. So now that we have that in place, and it looks like I did import the wrong one, so not this one, but instead, so if I import this again, so we have the one from Spring Framework, just like that. So now that we have this in place, I can say Rabbit MQ template dot and then set message converter. And this is so that we can basically send messages as JSON. So when a producer sends a message, this message will be sent as a JSON blob. And then on this side, it will also take the JSON blob message and then convert to whatever object it wants, right? So we send an object that gets converted to JSON. And then on this side, the JSON blob gets deserialized to a Java object. And inside, I can say new and then Jackson to message converter. And in fact, if I extract this to a variable, so I can say Jackson message converter. And this, so this is an interface. So I can say message and then converter, and make sure that you choose the one from Advanced Message Queue Protocol. There we go. And what I'm going to do instead is, let's just grab all of this, and I'm going to say public and then message converter and choose this one. So from AMQ support, and then I'm going to say Jackson and then converter. And let me just paste this right here. And if I put this on a new line, so you see everything. There we go. And what I want to say is just return and then Jackson message converter. Now, the benefit of doing this way, and also we have to annotate this with @bin in here. And basically inside of this converter here, you can pass a JSON object mapper. And with a JSON object mapper, what you could do is, if you want to have specific modules that you want to use, you can just say Jackson and then to object mapper builder dot, and then have a look. You can say JSON, XML, and you can basically keep on. If I say JSON here, I can then say, for example, modules, and you can configure this the way you want. But for now, all we want is a simple message converter, and just return that. Now in here, we can just say Jackson and then converter. And all we need to do is just return and then Rabbit and then template. And finally, let's annotate this with @ and then bin. Next, let's go ahead and define the listener. So we have configured the Rabbit template that allows us to send messages. Now, in order for applications to consume the messages from the queues, we need to set up the listener. And to be honest, so that you know, you actually don't have to set this up, but because I want you guys to learn things the right way, so that you understand how things work, so I feel like it's best practice. So the same with the template right here. So by default, you can just inject and one is provided to you. So here I'm going to say public and then simple Rabbit MQ listener container factory. And let me just have this long name in here. There we go. And inside, let's just say simple rabbit listener container factory. This will be called factory in here, equals to new. And this is as straightforward as this. Let me put this on a new line so you see everything. Now we need to basically, so let's just say factory dot set and then connection and then factory. Now, if you remember correctly, before we have this connection factory, so let's just use it. So connection and then factory, and also let's set up the message converter. So factory dot set and then message converter, and then we have the Jackson message converter, and finally let's just return. So return and then the factory, and as always let's define, or actually let's just say that this is a bean. Now we have configured the template, so this allows us to send the messages to the queue, and this allows us to receive the message from the queue using the Jackson converter. And if we have to change, so in here, so we can pass the object mapper in here, so JSON object mapper. So if we have to do that at a later stage, we will do it, but for now let's just leave this as is and move on. But this is pretty much the setup required for us to send and receive messages from queues. Now, obviously, this is not enough because we haven't set up the exchange nor the queues, and we didn't actually bind the exchange to a particular queue. So that's what we're going to do next. Now that we have this module, which is almost ready, so we have the template, the listener factory, and the Jackson converter. Now, what I want to do is to add the dependencies to our notification microservice. So customer will send a notification to this exchange, which we're going to set in a second, as well as the queue. Now we need to set up the dependencies for notification as well as customer in here. So let's together open up IntelliJ, and let's open up the project tab. Now navigate to notification and then pom.xml, and in here let's just add the dependencies. So first we need Spring and then boot starter AMQP, so or advanced message queue protocol, this from Spring Boot. We also need the dependency that we've just created for our module. So dependency, and this will be advanced message queue and then P, and this comes from Amigos code, and leave the version as 1 and then snapshot. And to be honest, this is it. So let's just take these two dependencies and let's pretty much just add them to customer. So customer will also need this. So here, let's just add to customer. So at some point, maybe fraud might want to interact with the message queue, but for now, I don't have any intentions to do so. And I just want to focus on customer and notification for now. So now let's just click on this button right here to load all the Maven changes. And to be honest, this is it. So you can see the power of having these modules, and then we can just include the dependencies wherever we need them. So go ahead and open up the notification module, and inside open up the application.yaml, and at the very bottom, let's go ahead and define the properties for how to connect to our queue, including the exchange as well as the routing key. So in here, go ahead and type rabbit and then MQ column, and then let's have exchanges. And for now, we're going to have one exchange called internal, and we're going to name this as internal dot and then exchange. Let's also define the queue, and the name for the notification queue will be notification dot and then queue. There we go. And finally, we have to define the routing and then keys, and currently we just have one, so internal dash notification column, and I'm going to name this as internal dot notification dot routing and then key. So if I put this full screen, so exchanges or internal is this one right here. So this is what we are defining, this topic exchange. So we are giving it a name. Then the queue, so let's just say that we are specifying the name for this particular queue right here is this one. So notification and then queue. And then the routing keys is how we're going to tie the exchange to the queue using a binding. In a second, you'll see this in action. And in here, let's create a new and then class. I'm going to name this as notification and then config. And I'm going to annotate this with @ and then configuration. And inside, we're going to need the following. So here, I'm going to say private and then string internal and then exchange. And the value for this will come from rabbit MQ exchanges and then internal. So let's just say @ and then value. And here, let's just use $ and then curly brackets. And then this will be rabbit MQ dot exchanges dot and then internal. Now let's take this right here and let's do the same for the queue. So rabbit, and then this will be queues, and the queue name is notification. So here, just say notification, and let's rename this to notification and then queue. And finally, in here, we have the routing keys, internal notification. So let's just take this name right here, and in here, let's just paste the exact same thing before, but instead of exchanges, this will be routing dash and then keys. And instead of internal, this will be internal notification. And here, I'm going to say internal notification routing and then key, and delete this. Now let's define the getters for these, and off we go. So you can see that now this is much easier for us to manage these values. So if you want to deploy to a different environment and you want to change these names, so you just change it here and off you go, instead of having to change the class itself. So this is why we should be using configuration classes and application.yaml or application.properties. This is one way of doing things, but obviously there are many other ways that you can work with configurations, but this is more than enough for what we are doing. Next, let's go ahead and define the queue exchange as well as the binding. Let's define the topic exchange. So this is the actual exchange, as well as the queue and the binding. So the binding is what ties together the exchange to a queue, because you can have multiple queues bound to one exchange. So currently we've named this as our internal exchange. So let's go back to IntelliJ and let's begin by defining the topic exchange. So in here, right after the fields that we have, let's have a public. So let me put this full screen. So public, and then here I'm going to say topic and then exchange, and then internal topic exchange. And here we're going to say return new and then topic exchange, and the name will be this dot and then internal exchange, right? So this is what we've defined in the application.yaml in here, this one right here. Next, what we need to do is annotate this with @ and then bean. Now let's define the queue itself. So this will be public and then queue. And again, make sure that this comes from amqp.core from Spring Framework. And here I'm going to say notification and then queue, and inside return and then new and then queue, and this will be this dot and then notification queue. So this is the name of the queue. Now that we have the exchange as well as the queue, so exchange as well as the queue in here, so let's just say that it's this one right here. Next, what we need is to bind these two together. To do that, we need to, and actually I forgot to say at and then bean in here. So if we want to bind these two together, we have to say public and then binding, and make sure it comes from the same package, and then internal to notification binding, and let's just say return. Now we can use the binding builder dot bind the queue, so notification queue, and let me put this on a new line. So we're going to bind the notification queue dot to the exchange, and our exchange is this one here, so internal topic exchange. So internal topic exchange and dot with, and then the way that we put the two together is by using the routing key. I'm going to say this dot and then internal notification routing key. So this is this field right here, which comes from here. And to be honest, it's as simple as this. Last but not least, let's annotate this with @bean, and we are good to go. So let me know if you have any questions on this, but all I'm doing is basically setting up the exchange, then the queue, we have the binding, which is done with a routing key. If you have any questions, drop me a message. Otherwise, let's move on. Now let's build the functionality that allows any producer to send messages to any topic exchange. So within this same package, so com amigos code amqp, let's just create a new class. And in here, I'm going to name it as rabbit mq message producer. There we go. And in here, let's annotate this with @ and then component. We also want to use SLA4j to log a few things. And inside, let's say private and then final AMQP template, which we have configured in the previous video. Let's also say @ and then all our constructors. And now what I want to do is have a simple method. So I'm going to say public and then void and then publish. So we're going to publish an object, and this is because we're going to have different types of DTOs in a second. But in here, let's just say object, and then this will be the payload. We also have to define the exchange that we want to send this to. So this will be string and then exchange, and let me put this full screen. And finally, the routing and then key. Now, to send to the exchange is very simple. So all we do is we say template dot, and then we have a bunch of methods. So we have convert and send, we have send and receive, so on and so forth, including the type. But what I'm interested is this one right here, where we pass the exchange. We also need to pass the routing key, because remember, we have the exchange, and then the routing key right here is what binds to a particular queue. And finally, what we need is the actual payload. Just like that. And it's as simple as this. Now let's have some logging in here. So just before we send, I'm going to say log dot and then info, and then inside publishing to and then exchange using routing key, and then I'm going to say payload, and then this is the payload, just like that. Now here I can just basically say exchange and then routing key and then the payload. There we go. And finally, let me just duplicate this, and I'm going to flip this around. And what I want to do is, so I'm going to say published. So I've got some logging before and after. And to be honest, this is it. So we have now this class that allows us to publish to an exchange by passing the exchange name, as well as the routing key, and finally the payload, which is an object. And this is an object because we want to be able to send any payload. If you have any questions, drop me a message. Otherwise, let's move on. So within RabbitMQ, you can see that we have got no connections, we've got no channels, no exchanges, so only the default ones, no queues, and pretty much we wrote a bunch of code, but we don't see nothing yet. Well, in order for us to see the queue as well as the exchange, we have to start notification. So what we need in order to start notification is the following. Within notification, what we're going to do is, let's open up the notification application. And what I want to do is to bring in, so these dependencies right here. So I want to bring this class right here. So RabbitMQ message producer, so that we can test whether we can send a message to notification MQ from notification. So in here, let's go ahead and, so here we need to say scan and then base packages. This will be com.amigos code. And then if I press Control space, we have notification, comma, and then here AMQP. So now it means that I can have, so let's just have a command line runner. And this command line runner will allow us to inject. So we want to inject a couple of things inside. So in a second, so return, and this is like this, args, and semicolon in here. This has to be a bin. There we go. So inside now we can inject the producer. So RabbitMQ message producer. And if I put this full screen, so let me just call it producer. And also I want to inject, so let's inject the notification config. So notification and then config and notification config. So what I want to do is the following. I just want to see whether I can say producer dot and then publish foo, comma, and then the exchange comes from notification config dot and then get internal exchange. Let's just put this on a new line, and then comma in here, notification config, and then get internal notification routing key. So hopefully this should work. So let's just put a breakpoint in here and let's start the Eureka server. There we go. And while this is starting, so let's open up notification, and we also have to specify where the RabbitMQ lives. So here, just say RabbitMQ addresses. And in here, so if you're running within a cluster, you can specify all the addresses. But in our case, remember, inside of docker.compose, this is a port 5672. So here, just say localhost and then 5672. There we go. And this is not HTTP, and it has its own protocol. And you can say, I think it's AMPQ, Advanced Message Queue System, column, and then you can specify this, but this should just work. And I've just realized that there is a typo, so this should be localhost. And now let's start notification, but in debug mode. So let's just put breakpoint there, and hopefully we should stop in here. So just give it a second, and I like to put this full screen because my font is quite big, but hopefully we should stop, create table, and off you go. So you can see that we've stopped, and now you can see that in here things are wired up correctly, and we are about to publish. So I just want to make sure that things were wired up correctly, but technically we don't need this breakpoint. So if I open up debug and then continue, go to console, have a look. Let's just have a look in here, and there we go. So we have a couple of messages, but what I want to show you is, if I scroll up, this is from our producer, this log line here, and it says publishing to internal exchange using routing key, internal notification routing key, and then the payload was foo. Then it was attempting to connect to localhost 5672 using the caching connection factory, then created a new connection using the rabbit connection factory, which you've seen before. And then finally we have published to internal, and this is our log. So the payload was foo, and we are good to go. So if I open up the RabbitMQ management console, and then in here, so if I click on queues, check this out. We have one message which is ready. So this is nice. Now, if I open up notification.queue, and in here, you can see that I can get messages. So I can get one message. Let me just say get the message, and ta-da, the payload is full right here. So we managed to send a message to our queue. Now let me go back and collapse this, and let me stop this in debug. So I usually don't run things in debug unless I need to, but what I want to do is, let's just have a record in here, and I'm going to say person, and this person will have string name and then int age, just like that. Now instead of foo right here, I'm going to say new and then person, just like that. And then the name, I'm going to say Ali, and then the age, let's say Ali is 18. So let's start the notification application once more, but this time without running in debug. And let's have a look at the logs. So you can see that it actually did manage to publish right here, right? So publishing, and then let's have a look at the payload. You can see this was the object, and then in here we did manage to send the payload. And by the way, this is what I was saying about the URL. So AMQ right here, right? So this is the protocol, but I've just said, so let me just show you before I forget. So in here, I've just said localhost, but if you want, you can use this right here. So this is the protocol. But anyways, let me close this. Let me open up the management console for RabbitMQ. And now if I click on queues again, we have two messages which are ready. Let me go into this queue. And if I get message, I only get foo, but I can say, give me, let's say 10 messages, get, and you can see message 1 in here is foo. Message 2 is, have a look. This now is a JSON payload, and this is what we have configured in our backend. So this is working beautifully. Now, obviously, I don't want to do anything with these messages. So what I'm going to do is I'm going to say purge messages. So basically, we won't be able to recover these messages, but that's fine. And this is now purged. And if I click on queues, and then you can see that actually, I don't think this is right, but let's just go inside, get messages, and you can see the queue is now empty. Finally, I'm going to close this and go back to IntelliJ, and inside of this main application, I'm just going to comment this so that if you